Let's start chapter 8.3, which is about sums and integrals and comparison theorems. We said before that there's no formula for the sum of 1 over n to the p when the sum converges, like if p equals 2 or 3 or 2.5 or something. There's also no formula for the sum if you stop before infinity of 1 over n to the p, even though it's easy enough to integrate 1 over x to the p or 1 over t to the p. Somehow there's a difference between how easy it is to get an answer for the integral versus the discrete sum. So let's take a look at the relationship between those two. Here I have a spreadsheet set up to start at 1, 2, 3, 4. Here's 1 over this value to the p, and then here's the running sum so far, so s of 1, s of 2, s of 3, and then here's the value of the antiderivative minus the antiderivative at our starting point. And then we're taking the difference between the value of the sum so far and the integral so far. So let's see what happens here. We're using p of 0.5. Think whether that sum is that series is going to converge or not based on the p-test. Well, the p-test says if p is less than 1, then less than or equal to 1, then the series will diverge. So we know the ultimate answer, these s sub n's are going to go to infinity, but we might be interested in the value of the sum before we get to infinity, and we can compare it to the integral. So let's go look at our graph here. The blue is the individual sequence terms, a sub n. The orange is the sum so far, and this gray line here is the integral so far. So what do you notice about how the orange line relates to the orange line, which is the sum so far, relates to the gray line, which is the black line, I guess, which is the integral so far? Let's try a different value of p. How about 0.2? That seems to diverge even more quickly than when p was 0.5. How about 0.5? 0.9? Seems like they're kind of close. I mean, we can definitely see a gap here, but it's a gap of something less than 1 out of 6 or 7, so we're only off by, I don't know, 20% or so, maybe less. We can also put in values above 1 here, so how about 1.1? They still seem to be behaving mostly the same, and we can look at how their difference is behaving, and that seems to be about just a little above half. We could try p of 2. There we're still seeing, now we're seeing a larger difference, but they still seem to be behaving roughly the same. Actually, the difference isn't that much larger, it just looked larger because the y scale of the graph changed. And then if I put in a p-value of 1 here, the summing will go fine, but the antiderivative fails because I divide by 0, so I've got another sheet that only handles the p-test or the p-series when p equals 1. And we can see, a lot like the other graphs, that the sum is always above the integral so far. And let's go look at the difference between the two. Seems to be decreasing. Now the square root of 3 is, square root of 1/3 is 0.577 something. Let's look at what that is. Square root of 1/3. 0.5773, so this looks like it might be decreasing toward that. But if we jump to like the 10,000th term, it's actually a little bit below the square root of 1/3. So it does seem to be converging to something. So this is the difference between the sum of the harmonic series so far and the integral of 1 over x so far. It seems to be converging to 0.577 something. And that's actually a famous number in math. It's called the Euler-Mascheroni constant. And here it is to a bunch of decimal places. So it's just slightly less than 1 over square root of 3. It's a big important number in math that maybe you haven't heard of, but look at all these places that it pops up. In fact, it's so important that when babies turn the Euler-Mascheroni constant years old in my family, we have a little celebration. I'm not sure why they're not looking very happy here. Anyway, let's go back to paper and pencil and recap what we talked about. So we said in Excel we saw that the partial sum of p-series was always greater than the related integral, and it was greater than, but not a whole lot greater than, and it was a pretty good approximation, it seemed. And we saw for the harmonic series in particular, the difference between the partial sum and the integral goes to something famous called the Euler-Mascheroni constant, gamma. So what are some good follow-up questions here based on what we saw? Well, think about that. Asking good questions is a big important thing in math. So what questions should we ask? We might ask, why did we see all that? Is it trustworthy? Like, we only saw it up through term 100, or in one case, and term 10,000 in another case. Just because we saw it for the first 100 or 10,000 terms doesn't mean it's always true. So can we trust it? Another good one is, this was for p series, 1 over n to the p. Is it true for other series as well? I mean, if it's even true here. Not just 1 over n to the p. So those are some good questions that we will talk about in future videos.